Hello, and welcome to the ALCF's Getting Started video on Theta and Cooley. I'm Chris Knight, and one of the team leads for the ALCF Catalyst team. The intention with this slide deck is for it to serve as a self-contained, quick reference guide to help users with setting up their software environments, compile codes, and submit jobs. In many slides, you'll see pointers to the ALCF user guides, where you can view additional details and discussion of their various topics. After covering system overviews and several key topics for the Theta and Cooley resources, I'll then spend some time discussing general tips for troubleshooting issues before concluding.
Theta is very much a bridge between the Mira and the upcoming exascale Aurora system. And here the emphasis is on all three categories of simulation, data, and learning, and enabling those at scale. And using Theta today as a means to get projects ready for tomorrow on Aurora. It's a Cray XC40 system running the Cray software stack, 11.7 petaflops peak performance, 4,392 nodes of the second generation Intel Xeon Phi. This is codenamed the Knight's Landing. The core is running at around 1.3 gigahertz. It depends if you're running heavy with AVX 512 instructions or scalar code for the dynamic frequency. And each core has 4 hardware threads. Memory, there's a lot of memory on these nodes if you're used to some other architectures. 192 gigabytes of DDR4 and 16 gigabytes of what is referred to as the MCD RAM memory, high bandwidth memory. And I'll say a little bit more about that in a couple of slides. And also attached to each node is a 128 gig solid state drive. And so combined with the large amounts of memory and the solid-state drive, it really does offer some unique capabilities in terms of data and learning, and also in the simulation space. The network, Cray Aries high-speed interconnect, Dragonfly topology, and of course, the project file system is a 10 petabyte Lustre file system with approximately 210 gigabytes per second throughput. A little more closer look at the full system. At the smallest scale, a single socket KNO node, 64 cores, 4 hardware threads per core. 4 of those nodes make up a compute blade. 16 of those compute blades form a chassis, which is essentially 1/3 of a rack. And so 3 of those chassis will constitute a full rack of Theta. And 24 of those cabinets make up the full system. And so all together is how you arrive at the 4,392 KNO nodes, 1,152 Aries switches, 12 groups. If you're concerned about, if you're interested in properties of the network, the Dragonfly topology, there are 12 groups on the machine, and total bisection bandwidth of 12.1 terabytes per second. And so again, a lot of memory, a lot of solid-state disk drive on the machine. And so this really does offer, again, to repeat myself, some unique capabilities in the data and learning space, as well as simulation. A little more details on the memory modes. This is one of the things I think that is unique to the KNL. There are the 2 types of memory on the node. There's the DDR4 memory and the high bandwidth memory. And your application can access these memory address spaces in a number of ways. In cache mode, you can access a single large memory space with the DDR feeding to the in-package memory at 90 gigabytes per second, and the CPU accessing the in-package memory at 480 gigabytes per second. And so in cache mode, you get access to all of that memory and this is one means by which an application can make use of all of the memory on a node without any changes to the source code. In flat mode, you are explicitly setting control over how memory is allocated. You can explicitly allocate into the DDR4 memory, the slower memory, or you can explicitly allocate into the high bandwidth memory. And examples of where an application may do that is if many of your kernels are not memory bandwidth sensitive or bandwidth limited, typically you can allocate those arrays into the DDR4 memory. And then you can save the high bandwidth memory. You can allocate those to the DDR4 memory, which has a lower latency. And so for arrays that do feed into kernels that are higher memory bandwidth limited, you can then allocate those arrays out of the high bandwidth memory. An example may be fast Fourier transforms. Typically, for those arrays, you would want to allocate those out of the high bandwidth memory. And it may be the other case for other arrays, maybe more compute-intensive kernels, where certain arrays are principally used. You could allocate those out of the DDR4 memory. And then there are also hybrid modes where you can allocate some percentage of the in-package memory as a cache. There's much more detail in all of the different configurations that are available on Theta, are available at that website. And so users, through their job submission, have access to all of these modes if you want to explore performance impacts on your application. I'll say more about that in several slides later. The Theta is a typical Cray programming environment. Much of the same software that you may be familiar with if you've already run on a Cray system. There's Fortran, C, C++, Python compilers. There's a handful of programming models, distributed memory, shared memory, global arrays. OpenMP is available in the system, PGAS. A number of tools for debugging and for performance, and for a couple of porting tools. Optimized scientific libraries. If your application is dependent upon, BLAS, DGEMS, GLAPAC, the related fast Fourier transforms, there's a handful of options available. You can use Cray's libsci, MKL is available, and a handful of other libraries are also available. And if you choose, you can build your own. And also a couple of I/O libraries. For navigating the system, a number of things are located in /soft, and so that is a directory structure where you can peruse. Typical directories are there's compilers, debuggers, libraries, perf tools, and also visualization. A number of those are enabled via the use of modules, which I'll get to on the next slide. But those directories are there. And then there are other things. If you're using a handful of community chemistry codes, there's a soft applications directory that has a couple of applications in there as well. And a lot of these softwares and libraries are labeled or listed on the ALCF website. Additionally, there are a number of machine and deep learning and workflow software and libraries available on the machine. I won't go through the full list, but you'll notice that a handful of these do have been selected for presentations at the workshop. Many of these tools and libraries are optimized with performance libraries such as MKL or MKL DNN. There are a handful of workflow and data analysis tools. Singularity Containers is one example. Balsam for workflows. And there's a handful of Python installations as well. Cray, Intel, and Anaconda. And so many of these are accessible through the modules. And modules is how we control the environment on the system. If you're not familiar with modules, there's a website up there that you can go to for a quick recap. We also have a lot of information on the ALCF website. Basically, this is a tool for managing your user environment, for loading paths of certain applications into your path, setting up paths for the different libraries that you may be linking. This is also the key mechanism by which you can change the compiler that you have in your environment. A handful of useful commands. You can do module help that'll list all of the available module commands. You can see a list of what's currently loaded in your environment. So this is something that you could do when you first log into the machine to check what your default environment is. You could do module avail to see the long list of all the modules that are available. You can add a module to your environment with module load and then the name of the module. And you can also remove a module with the unload argument. For certain modules, you may want to swap them instead of explicitly loading and unloading. So you can then use the module switch, the old mode, maybe that's the current compiler in your environment, and then followed with the new module, which may be the new compiler that you want to switch to. Maybe you want to switch from an Intel compiler to the GNU compiler. So using module switch is one mechanism to do that. And if you want to see additional information about what that module and how it changes your environment, you can do module show in that module. And then you'll see an outcome of all the commands that are executed to update your environment. For compiling, There are a handful of Cray compiler wrappers that are needed to cross-compile from the logit nodes to the Theta compute nodes. And so it's really critical when you're building your application for the compute nodes that you use these wrappers, the lowercase cc, uppercase cc, and for Fortran, ftn. Do not use some variant of the MPI, cc or F90. These will not generate code for the compute nodes. And again, as I stated on the earlier slide, if you want to switch compilers, you can use module switch or module swap. They offer the equivalent functionality. And so I have examples of the Intel compiler is loaded into your environment by default. You can switch to the Cray, GNU, or the C-Lane compilers using the appropriate swap command. The Cray MPI the Cray wrappers. They do a lot for you, and depending on the application that you're building, you may want to know more about what that Cray wrapper is actually doing. And so if you're running into issues and you think it may be something related to how you're using the compiler, you can see explicitly what is being invoked with the -cray pe-verbose command, and this will give you the full list of options and headers and libraries that are being used on that command. Sometimes for your application, you may not, so by default, the Cray compilers will load Cray's libsci math library, and in many cases that's more than sufficient. And in other cases, you may not want that, or you may want a finer grained control over what gets linked in for maybe your BLAST, your SCLAPACT, your FFTs, etc. And so you can disable that automatic linking with module unload Cray libsci, so that no automatic linking of a math library will take place. And then on your link line, you can then explicitly link in math libraries in the order that you'd like. I do this sometimes when I'm mixing MKL with other libraries and libsci. So you've got onto the machine, you've navigated the software environment, you know where all the libraries you are needed to build your application, and you successfully compiled and built your application. And now it's time to prepare submitting a job. First thing to do is make sure that you're a member of an active allocation. Everyone in here should be a member of an active allocation. If not, your original project, the one for this particular workshop, the SDL workshop. In general, what can happen near the end of an allocation is when people may run into problems with a negative balance. And so checking the projects in that situation is a good first step to see, is your allocation still active? One good thing to be mindful of is disk space. You really don't want to submit a very important job, have it wait in the queue, and then the job fails because you ran out of disk space. And so good things to do. Maybe you're doing something in your home directory. I don't encourage that when you're running a production job, but maybe you are. You can use the myQuota command to check the quota of your home directory. For your project directories, you can run the myProjectQuotas command to see the full list of all project directories you're a member of, and to get a sense of how near the quota limit you are, and if there's enough space available for your job. And really to stress, the parallel file system is what you want to run your jobs out of, and that's the project directory for your particular project that you're working on. And that's really where you want to run the bulk of your calculations out of. And then lastly, checking to make sure that you have enough hours in your allocation. It is good in terms of having priority in the queue to have a positive allocation for your project. And the tool to query those types of questions would be the SBank tool. And so there's a lot more information on the SBank tool at the website on the top of the slide. A few useful commands are listing the allocations for the project that you're a member of. And it may be a little hard to read, but there's SBank, and then the letter L, and then the letter A for list allocations. If you're maybe the PI of a project and you want to get a detailed report for a particular user, you can then add on the option for -U and the user. And a comment that I'll make is that in general, charges for jobs that are submitted are based on the node count, with the caveat being that 128 nodes is currently the smallest allocable unit. And so if you submit a job for 256 nodes, you'll be charged for that 256 nodes, whether or not your job actually uses those nodes. If you submit a 16-node job to the default queue, your job will get allocated 128 nodes. And so although your calculation is only running on 16, you'll still be charged for the full 128. And I'll have a few words near the end on how how you can make the best use of in that case. So continuing on with Cobalt, this is the resource management software that we use on the ALCF systems across all of the systems. If it does have syntax that is similar to PBS style scripts, and you may be familiar with some of these commands. If you want to submit a job, you can use the qsub command. And I'll comment that all of these have man pages that you can look at for additional detail. You can query the status of your job with qstat. You can delete a job with qdel, followed by the job ID. You can alter the parameters of a job using qalter. Maybe you submitted a job, it's accrued score for a while, and you realize that you need to extend the wall time, but the job hasn't started yet. You can use qalter to extend that wall time, and you'll continue accruing score at that point, after that point, without losing any score. Maybe you submitted your job and you realize that you really want the job to move in a different queue. And a good example of that would be this workshop this week, that maybe by default you submit your test job and it goes into the default queue, and you wonder why it's not starting. But then when you look at the status, you see a bunch of idle nodes. Many of those nodes may be idle nodes that are reserved for this workshop. And so then you would use qmove to take the job that you had accidentally submitted to the default queue and move it into the workshop's special queue. Maybe you've submitted a job and you realize there's a big issue. Maybe the input's not ready or something else. And so you can use qhold to place that job on hold. It'll stop accruing score at that point. You can fix whatever the issue may be, and then you can then release the job to continue accruing score from where it left off. And so the alternative would be then deleting the job, losing all of the score that you've accrued, and then starting fresh. And so qhold and qrelease, if used sparingly, may be a good alternative in that case. For submitting your job, there's a number of options that can be specified. Some have good defaults, but many I would explicitly set. That's my advice. The project that's going to be charged for the job that you submitted, you'd want to use $A. This is an example where it will pick a default project if you don't specify the project, but that may not be the project you want allocated for that job. So it is good to explicitly set this. -Q, the default for -Q would be the default queue. In general, that works fine on Theta, but there may be reasons to explicitly set it, and so I would encourage explicitly setting it. The maximum wall time for your job, -T, and you can specify the time in minutes, or you can give an hour, minute, second, an hour, minute notation. The number of nodes allocated for your job, -N. The number of processes, --proc count. Sorry, some of this is a typo from the BlueJean queue. There's more information on the next slide. But -O to have the file prefix for some Cobalt log files that are generated. If you'd like a notification for your job in email when it starts up and when it completes, you can use -M followed by your email address. And then one important option is -- dependencies. So I point this out that even if you've been running on the systems for a while, this may be an option that you've forgotten. If you find that your workflow, you have a long sequence of jobs, but the second job can't start until the first job completes, the third job can't start until the second job completes, and so on, I would highly advise making use of the dependencies to improve your throughput through the queue with score boosts. And finally, -I for an interactive job. Maybe you want to log in to not necessarily the compute nodes, but a service node, and interactively submit jobs while you're debugging an issue. So that's something that I frequently use when I'm debugging issues on the machine. I submit the job once, get onto the system when my nodes have been allocated, and then I can run multiple app runs within that interactive job. Jobs are submitted on Theta with a job script, and inside of that script, it is the aprun command that is used to actually launch the application onto the compute nodes. And so this is a relatively simple example of my script.sh. This is an executable script. And so if you go to qsub your script and you get an error message about your script not being an executable, executing the change mode command to make it executable will fix that. A couple of lines near the top start with the pound Cobalt. And so these are setting the Cobalt's qsub parameters right in your script. And so the alternative to doing this would be to have your qsub command followed by a long list of options. The alternative here is that you can specify those options within your job script, and it's just one more way of having a record of what you submitted in that case. And so the good defaults, -A for the project, -T for the maximum wall time, -N for the number of nodes your job is being submitted on, -O if I want to change the output of the name of the output from the Cobalt logs, and then the Q. The line below that is specifying the memory mode. And so the default memory mode a job will be allocated to would be in cache quad mode. It's good to explicitly set that so that you can ensure that that is the memory mode that you're requesting, and that's accomplishable with the attributes flag. And then there's an echo command, and then the aprun, and then aprun is where your application is getting launched. You could specify the total number of MPI ranks for the job with -n. You specify the number of MPI ranks per node with -N. And then the section that follows afterwards in that box are settings to control the affinity on the node. And so -D, -J, and the --CC are three arguments that you'll use to control how you want MPI ranks and threads placed on the machine. And we'll go through a couple of examples in a couple of slides. The aprun settings are followed by your application, the executable, and then any application arguments that you may have. A quick overview of the aprun and its options. A lot of this information is available on the website with additional helpful hints. I'll say that the -D. So to repeat, -n is the total number of ranks for that aprun instance. -N is the number of MPI ranks per node for that instance. Controlling the number of hyperthreads available per an MPI rank is controlled by -D. And so this is effectively -D is controlling the spacing between MPI ranks. If -J is controlling the number of hyperthreads that are active per core. And so again, with the KNL, you have potentially 1, 2, or 4 hyperthreads that can be running for your application. And you'll use -J to control whether 1, 2, or 4 of those threads are active for your application. Environment variables are specified with -e, and then the environment variable that you'd like to set. And then one parameter that I do encourage using if you are not using all of the threads for your application is -R for core specialization. And so this will shift things like the OS processes off to a single hyperthread that the application is not using. And this is one mechanism to help reduce variability in your runtime, at least on the on-node sources of variability. And if you're getting started, a couple of environment variables that you may need, -E, OMP num threads, if you're running an OpenMP multi-threaded application. You may want to control the affinity by some other means, like KMP affinity. And so in that case, you would do --CC none to tell aprun that you want to control the affinity by some other means, and then KMP infinity with the appropriate settings. Now, a couple of aprun examples. And so the first example here is motivated for an MPI-only type of an application. And so Theta's KNL nodes, they have 32 tiles each. And so that's how you get 64 cores. You have 2 cores for each of those 32 tiles. And again, each core has 4 hardware threads. And so in this simple example, we're going to run a 2-node calculation with 64 ranks per node. And we'll only have 1 thread per rank and 1 rank per core. And the aprun setting for that process is listed below. And what you can see is with -J equal to 1, we only have 1 hyperthread active within a core. And so that's what the images are representing, is that you have a tile. I'm showing 4 tiles in this example, and then the ... would be the remaining tiles. Within each tile, there is the 2 cores. And then you can see the black crosses is trying to denote the individual hyperthreads within a core. And in this example, dash J is 1, and so then only one hyperthread is active per core. Dash D is 1, and so the MPI ranks that we're going to lay out are spaced apart by a single active hyperthread. There are 64 MPI ranks active per node, and so then the first 64 processing elements that are formed by the D hyperthreads would be assigned as the master rank, or would be assigned an MPI rank. And then you can check the affinity with an example. There's an affinity example that I'll show up that you can see a path to at the end of the talk, where you can check to make sure that did you supply the right aprun settings and get the process layout that you were expecting. And so if you're new to the KNL and or the aprun command, it's a good exercise to check the affinity for small test cases. In the second example, and in this example, again, we're running with 2 nodes. In this case, we're going to run with only 32 MPI ranks per node. We're going to run with 4 OpenMP threads per rank, but we're only going to use 2 hyperthreads per core. Depending on your application, you may see additional benefits by using all 4 hyperthreads. And so that's a good thing to check is, how is your performance impacted by 1, 2, or 4? And in general, you may see performance, if you're very compute intensive, limited at 1 hyperthread per core, or maybe you'll see a small boost at 2 hyperthreads, maybe even 4. And so in this case, you can see that dash J is 2. We're going to use 2 hyperthreads that are available for each core. Dash D is 4. And so that's indicating that the MPI ranks are going to be spaced by 4 hyperthreads. And so with this layout, we see that the MPI ranks are going to be placed on the first active hyperthread of a tile, and that the OpenMP threads for each rank will be shared on that tile. And you can see the ordering. The ordering is 0, 1, 2, 3 in the order of the cores of the first hyperthread. And then the process repeats with 64, 65 for the second hyperthread of each core. And then the affinity output below. And so most of the affinity output here is being generated with a toy example that I have at the end of the slides. And so if you want to explore this, you could grab that example that I'll show the path to and run some experiments like this. And so this would be a good opportunity for an interactive job. You submit one interactive job, get onto the system, and then you can run multiple app runs with different settings to check the affinity to get the process placement that you do desire. And so a quick overview to repeat a few things, but just to call more attention to them. With app run, you can use dash D and the dash CC depth to let app run have control over the affinity, which you can then control as in the examples I just showed. If you would like to control the affinity by some other means, you can use dash CC none, and maybe you can use OpenMP or the KMP type environment variables to control the affinity by that means. Core specialization, you can activate that with the dash R, and the idea here is that you'll set the idle threads that your application is not using can be allocated to handle processes like the OS jitter and an MPI. And again, this is one mechanism by which you can try to reduce variability for the on-node portion of that on-node contribution to variability. One more comment on the memory mode. You can, if you are allocating, if you're requesting nodes in flat mode and you want to explicitly allocate to either the DDR or to the high bandwidth memory, you can specify that control with NUMA control. You can use dash M to have mandatory allocation into NUMA control 1 in this example. 1 is the high bandwidth memory, 0 the default is the DDR4 memory. Or you can have a preference. And so the difference with dash M is if you run out of memory in that space, the application will exit with an error. You can prefer allocation into one of the spaces. And if you run out of memory in that space, you'll fall back to the other available space. And you'll want to place the NUMA control and its arguments. I typically place it at the end of my app run arguments, but before the application. So if you're running your application in flat mode and you want control over the memory mode or how memory is allocated by default, you can specify it with that. So you've figured out, you've got your code compiled, you've figured out how you want to submit your job into the compute nodes, and you've qsubbed your job, and now it's submitted. One of the first things that you'll probably do, and I'm notorious for doing this, is I want to check the status. Is my job submitted? Is it, what's the status of it in the queue? And so the qstat command is what you'll want to use for that. And so you can run qstat, and you'll get a full listing of everything that's queued on the job and all the various states. Some people may find that the default output generated can be overwhelming. There are many columns generated, and so I offer one piece of advice that you have with qstat the control over to customize the output that you see. And so in this example, I'm using the -- header flag to specify that I only want a subset of available columns. And if you look at the man page, you can see the full list of everything that's available for printing. And so in this example, I'm looking at the job ID, the user, the maximum wall time submitted, the number of nodes requested, the state of the job, running, the job is running on the compute nodes, queued, the job is waiting for nodes to be allocated to it. Starting is another state that you may see. If the jobs you've requested are all in the memory mode that you've requested, the starting state, the time that it's spent there, may be relatively small. If, on the other hand, the memory mode that you've requested, the nodes need to reboot to get you that mode, you may be in the starting state for up to 15 minutes or so. And so I'll mention this again later, but that's one thing to be mindful of if you notice that your job's in the starting state for several minutes, is that it is starting, it's just waiting for nodes to reboot in the memory mode you've requested. Your job's queued. And so if you want to see the full detail of your job, you can use the qstat -f with the job ID. This will show lots of Cobalt specific information for your particular job that you may find useful. You can show everything that's listed for your job with the -fl argument. If you want to look at all jobs from a particular user, you can use -u, and then more likely you'll put in your user name in that case. And if you want to see information about the queues that are available on the system, you can use the -Q argument. And so if you ran this today on the system, you would see information about the SDL, the training queue. Again, if you want to delete your job from the queue for some reason, you can use the qdel command. If you want to alter the properties of your job, you can use the qalter command. In this example, I'm altering the maximum wall time of the job. So I use -T to specify the wall time, and then the new time that I want to set the wall time to, and then the job ID. The second example is altering the number of nodes that are available. And then the last example is maybe I want to move my job to a different queue. And so this week, a good example of that would be if you accidentally submitted to the default queue, you could move it over to the training queue in the system to increase your throughput in the queues. One thing that you can do, whether you're sitting at a terminal or you're on the bus, on your way home, is you can check the status of your job. And so if you go to the status.alcf.gov/theta/activity page, you can see a current snapshot of everything that's running on the system. Near the bottom of the image, there are tabs. You can select the running jobs, jobs that may be in the starting state, jobs that are queued. And an important one to be mindful is you can also check for reservations. And so as one example of, why are a bunch of nodes on the machine idle, you could go to this web page and click on the reservations tag, and you may see that a lot of those idle nodes are allocated for a reservation that's in place, like this workshop. Now, once you've hit qsub on your submission script and your job was successfully queued up, a couple of things will happen. The first thing that will happen is that you'll see the creation of a log file. And so this will happen right after your job is submitted, and it'll immediately have a small amount of information that would be helpful, on the job that was submitted. When your job enters the running state, you'll then see the appearance of two additional files from Cobalt, the output file and the error file. So output has all of the standard output directed to it, and error file has all of the standard error directed to it. You can use qsubs -O if you want to change the name of those files. A word on queues. So much more information about the queues on Theta are available on the scheduling policy for the XE40 systems webpage. I'll note that jobs are by default are routed to a single default queue. Nodes allocated to the job, they'll be rebooted if needed. One thing to note is that even though you're requesting the default memory mode, it may be that the jobs you've been allocated were in some other memory mode. And so there's always an opportunity that the nodes may be rebooted for your particular job. And so it's good to pad for that, to account for that when you're submitting your wall time. And so, an estimate of, an additional 30 minutes is helpful to include. A piece of advice, we really encourage, if you see your job in the starting state for several minutes, please don't delete that job. What'll happen is those nodes are going to continue rebooting no matter what. They're already in that state. But when you delete your job and then you resubmit the job, you may potentially request a second set of nodes that don't overlap with the first set and trigger an additional reboot. And so it is good that even if you see it in the starting state for several minutes to go ahead and leave it in there, and it should eventually run after the nodes had rebooted. On Theta, the wall clock time limits are a function of the number of nodes requested. And so if you look on the web page, you'll see a tiered structure. Small jobs can run for a relatively short amount of time, a few hours, whereas the larger jobs can run anywhere up to 24 hours. And so the website is currently that, the minimum allocation is 128 nodes. And so again, if you were to submit a smaller job, you can submit that smaller job in the default queue, but you'll still be allocated and charged for the full 128 nodes in that case. And today, the capability jobs on the machine are considered those requesting 802 nodes or more. For small-scale development and testing, there are a couple of 16-node debug queues, and these are preset into the cache quad and the flat quad memory modes. And so if you're doing testing in one of those two modes on a small number of nodes, you can specifically set -Q to one of the debug queues to have an improved turnaround time. Again, there's a much more information on the scheduling policy and running jobs on those websites there. I've already, I think, repeated myself a couple of times on the 128 nodes, but if there's any questions about that, please do ask. If you're in the situation where the individual calculation that you want to run does not require more than 128 nodes, one thing to consider is, do you have a large collection of those types of calculations that you'd want to run? If so, there are a handful of paths forward to bundling those independent calculations together into a single job submission that you can then scale up that job submission to 128 nodes, or ideally to some larger node count. It can be as simple as, in some cases, it can be as simple as listing multiple aprun commands within your job script, backgrounding all of those processes, and then having a wait command to wait for all those apruns to complete. That would launch, n independent aprun calculations across your job's allocated nodes. For more complex workflows, maybe the dependencies between jobs that are submitted, there are tools available such as Balsam that may offer you that may facilitate some more complex workflows within a job script. And so there will be a talk later at the workshop, I believe, on that. And again, to reiterate. For long sequences of jobs where job 2 has to run after the first job and job 3 has to run after the second one, I do encourage using dependencies. When the lead job finishes, a fraction of the score that job had when it started will be passed on to its dependent job. And so there will be, it's essentially a score boost to help your throughput in the queue. So that concludes the bulk of the content I had for Theta. Were there any questions? I only have a couple of slides on Theta, on Cooley. Okay. And so a very quick summary of Cooley, which is another resource we have here at the ALCF. Cooley is primarily serving as an analysis and visualization resource. And so Cooley is mounted to the project file system systems on both Mira and Theta. And so a workflow that you might have is doing a lot of your computation for the bigger calculations on Theta. And then maybe you have some smaller scale analysis or visualization that you may not want to do that on Theta. You can do that on Cooley as another option. And so all of the file systems are mounted to allow that type of a workflow. Cooley is an x86 system of GPUs. It has 126 compute nodes. It has a peak performance of 293 teraflops. Each compute node has two 2.4 gigahertz Intel Haswell processors. That's 6 cores per CPU, 12 cores total. There's an NVIDIA Tesla K80 on each node. That's 2 GPUs per node. There's 384 gigabytes of CPU memory, 12 gigabytes of memory per GPU, and 345 gigabytes of local scratch space for each node. The FDR InfiniBand interconnect, and again, Mira's GPFS and Theta's Luster's project file systems are both mounted to this. Unlike Theta, Cooley uses soft environments to control the environment, and this is analogous to Mira if you've done work on Mira. Very quickly, there's additional information on the user guides for Cooley, but very quickly, there are keys in a .soft.cooley file that are read at login time. And so an example may be that you want to use the GNU compiler in your environment. And so within the .soft.cooley file in your home directory, you could add an invapich key. At the end of this file is the macro default, and so that default macro should always be at the bottom of your config file. Anytime you go to edit the .soft.cooley file, you can execute a resoft to refresh your environment given the changes that you've just made, or you could log out and then back in to have the environment changes take effect. And you can see the full complete list of all the environment keys with the soft environment command. You can choose the compiler via the soft environment command. So this is one primary mechanism that you'll use to change your compiler. You can also load Python interpreters this way. For non-MPI compilers, there's a handful of options, GCC, Intel, and CLang. Maybe you do, in fact, need an MPI compiler. Invapich and MPish are both available on this system. And so the keys that are shown here will pull in the latest version. For example, with Intel, this would pull in the 2018 version of the compiler and the invapich MPI library. Job scripts on Cooley, they are similar in structure to the job scripts on Theta, except instead of aprun, MPI run is being used. And so in this this simple example, it's a straightforward job script. The number of nodes is being determined from a Cobalt node file. The total number of MPI ranks, in this case, is being, is a function of the number of nodes available times 12 cores per CPU. You can choose whatever is appropriate for your application. And then the job would be launched with MPI run, -F for that Cobalt node file, -N for the number of MPI ranks, and then the name of your application. And you could specify additional environment variables and so on within the script. And then you would submit that script with, you could, again, because we're at a workshop, you'd use the training queue, the number of nodes on Cooley. This example has 5, running for 10 minutes, charged against the workshop's project allocation, and then the name of the script that you're executing. On Cooley, if the default queue is default, you can use this for small test jobs, large, long jobs. You could do up to full machine for, I think it's 12 hours if you need to for your analysis or visualization. There's also a debug queue for the shorter, smaller test jobs that have faster turnaround time. If your workflow that you're submitting needs access to a public network, you can use the pubnet queue. If you are using the GPUs and you don't want to load an X server, you can use the NoX11 queue. And similarly, if you want to check the status of your job on the system or just the state of the machine, you can go to the Cooley's activity page. Are there any questions on that? So again, the Cooley description was relatively short. There is a lot of information on the ALCF website if you have additional questions. So the last few slides are just a very quick, you've submitted your job, and it just hasn't started yet. And so a handful of things to consider are maybe there's a reservation in place, and that's why those nodes that you're viewing on the activity page don't seem to be running jobs. And so if you can go to the activity page and look at the reservation tab, or you can use the show res command to see what reservations are currently in place, or which reservations are currently coming up in the near future. Again, jobs that are on Theta in the starting state, it may be the case that the nodes allocated to your job are still rebooting into the memory mode that you've requested, whether it's the default memory mode or a specific memory mode that you've requested. It may be just that there are no available nodes in the requested queue. Maybe nodes are down, they're busy running other jobs. Nodes may be idle, but they may be draining for the job that's currently at the top of the queue. Or they may, in fact, be reserved, like they are for this workshop. Again, you can check the status with qstat. You can go to the activity page. Also, every Friday we do send a weekly updates email. We do advertise all of the upcoming reservations, like, for example, like this workshop or preventative maintenance. And so that is a good source of information if you want to plan maybe the next week or two out. And if you want to, you can get a list of the status of all the nodes on both Theta and Cooley using the node list command. And so I tend to use the node list command if I want to submit a small job, or not necessarily a small job, but maybe a medium or large size job. And I want to figure out what's the smallest wall time I can submit my job to. So if I want to submit a medium to large size job and I want a quick turnaround, I'll use node list to figure out how many nodes are idle and what that smallest wall time job I can fit. So maybe I can't submit an hour-long job. It'll take a while to run, to start. But maybe I can submit a 35-minute job, and that'll probably run right away. So I use node list a lot when I want to try to have a quick turnaround time on larger jobs. Theta, there's core files, which are our friend when we're having to debug issues. And so core files can be enabled on Theta. You can also use ATP, abnormal termination processing, if you'd like. If you're using the Cray compiler, everything is linked by default. If you're using the Intel compiler, you do need to add an additional library to your link line. And there are other debugging tools. And some of this, for example, DDT will be discussed at the workshop. You can use stat or full-featured DDT. And then finally, when things go wrong, we do encourage you to examine core files. It is best to save all 3 files that are generated by Cobalt, the Cobalt log, the output, and the error. There is a lot of useful information that's in there that can be used to help understand what happened for your particular job. You try to retain more of the important information, the job ID, the machine name, the copy and location of files, what the exact error message was. And if you're not sure what happened, a good first place to turn is that Cobalt log file. It's a number of times what can happen is maybe the job runs out of time. And so at the end of the Cobalt log file, you'll see a message that the maximum wall time was exceeded. And so that's a very, I think, a quick way to figure out some of the more straightforward issues. And always, please contact us if you're having issues. If you have an ALCF contact, or you folks here in the room during the workshop, please reach out to us. You can always send mail to support@alcf.ano.gov if you have issues. You can always call the ALCF help desk Monday through Friday during normal business hours, and we will